So let's take a look at B from the worksheet. So in 1B, which is the series from n equals 2 to infinity 1 over square root of the square root of n minus 1. All right, and like I said, you're going to have this sheet for the exam, so I want you to get practice using it. All right, so what we do when we encounter one of these, you might already have an idea of convergence or divergence, but we need to figure out what this looks like so we can decide what test we want to use from this sheet. Well, if that minus 1, make sure. Oh, there's another n in there. That's what's missing. Let me fix that real quick. There should be an extra n under this. So if that minus 1 was not there, this would look a lot like our P series. Okay, so what that tells me is I'm going to want to compare it to a P series, either comparison test or limit comparison test, whichever one we think is easier. And we got to figure out what to compare it to. Now this, we do the same that we did back when we were doing it with the proper integrals. The minus 1 is the thing that's keeping this from looking like a P series. So what I'm going to do is I'm going to just focus at the lead terms. These are going to be what makes the difference in this one. All right, so what that tells me is this thing is going to be very similar to n equals 2 to infinity. I'm going to forget about the minus 1. 1 over the square root of n times the square root of n. Let's clean that up a little. Okay, well, that still doesn't look like a P series. So the question becomes, what kind of simplifying can we do? Well, let's take a look. We're going to be able to use properties of exponents. And this is kind of the process you go through with these ones that you're going to use in a comparison test with a P series. You take your lead terms and you simplify as much as you need. So one thing that we need to figure out is how can we combine this? Well, I've got 1 over, for right now, let's leave this as a square root. We'll take care of this one in a second. But this is just n to the 1/2. So under that radical, I have n times n to the 1/2. When you multiply two things of the same base, their exponents add. So this would be like n to the 1st times n to the 3/2 and times n to the 1/2. So under that radical, what I'm going to have when I simplify is n to the 3/2. Now it's under a square root. Well, that's the same thing as raising it to the 1/2 power. An exponent raised to another exponent, we multiply. So now we do have a P series. This is going to be 1 over n to the 3/4. So we consult our P series. Well, if P is less than or equal to 1, it diverges. So this thing diverges by P series. So I know whatever comparison I'm going to do, I'm going to be testing this thing for divergence. Now, if I'm using the comparison test, I have to show that this is greater than this. Might be easy, it might not. So I'm actually going to go and use the limit comparison test and just look at the ratio of the two. And it doesn't really matter which one I put on top. All right, so we're going to use the ratio test, excuse me, not the ratio test, the limit comparison test. So the limit as n goes to infinity, I'll put this one on top. That's, again, that's arbitrary. Square root of n, square root of n minus 1 over, and I can just write it like this. This is fine. Or we can write it in terms of radicals. 1 over n to the 3/4. Now, because we're choosing this one, because we saw, hey, this one is kind of similar to this one, we know that this comparison is going to work out. So the first thing I'm going to do is flip and multiply. So we have limit as n goes to infinity of n to the 3/4 over. We might want to make a decision at some point if we want to keep these in terms of radicals or change them to fractional exponents. So let's go ahead and just do that now. So n times n minus 1 to the 1/2 to the 1/2. All right. So now we want to see, you know, we are going to have a L'Hopital's rule. Basically have an infinity over infinity case, but we might want to see if we can do any simplifying first. So one thing I noticed is I have a product here being raised to the 1/2. So this isn't absolutely necessary. We could do it from here, but let's distribute that exponent just to get rid of that set of parentheses. So n to the 3/4 over n to the 1/2. Sorry, that didn't come out very clean. N to the 1/2 times, and now this is going to be n to the 1/2. Here, n to the 1/2 to the 1/2, excuse me, n minus 1. It's going to be n minus 1 to the 1/4. All right. Now, here's why this is going to be nice for us. And guys, I picked this one out specifically because it is a tougher one. They're not all this terrible. I shouldn't say terrible. They're not all this like this. What I can do now, I've got two things of the same base. I'm going to bring this up into the numerator by switching the sign on the exponent. This is going to make our lives a lot easier. Because now what I have is n to the 3/4 times n to the minus 1/2 all over n minus 1 to the 1/4. Now remember, our goal is to get this limit to become some kind of non-zero constant. All right, this will actually work out really nice because basically n to the 3/4. Let's put this over on the side here so you can see what's going to happen in the next step. Times n to the 2/4, negative 2/4. Multiplying those, we add their exponents, becomes n to the 1/4. So when we do that, we get n to the 1/4. Apologies, my handwriting is not good today, as usual. Over n minus 1 to the 1/4. Now, both of these are being raised to the 1/4 power. And that 1/4 does not depend on n. So we're going to do two things. I'll do it in two steps. because I don't want you to miss what's happening here. So basically what we're going to do is we're going to raise n over n minus 1 to the 1/4 power. And we have our choice. We can calculate the limit first, because this is the only thing that depends on n, or we can calculate the limit to the 1/4. So basically what we're doing is we're looking at it like this. We're going to calculate this limit first and raise that number to the 1/4. Well, you could do this with L'Hopital's. The derivative just would be 1 over 1. Or you could say, hey, I've got n to the first over n to the first as far as lead terms. This is going to go to the ratio of their coefficients, which is 1. So this equals 1 to the 1/4, or 1, which is a non-zero constant. We compared it to a divergent. So our series, 1 over square root of n square root of n minus 1, diverges by the limit comparison test. Questions about this one? Again, I picked this one on purpose. It's not super trivial to see where to start, but there was a couple things I wanted you to see. Number one, I wanted you to see how I picked the test for comparison. I basically circle the lead terms of the top and the bottom, make that its own series, and then simplify so I know something about that series. The response to that is the reason we needed to is because I decided to do a comparison test, and I needed to show that what I was comparing it to was convergent or divergent. So to answer your question, if you're doing one of the comparison tests, because you have to compare it to something that's known, you're going to have to at least say that what you know is convergent and divergent and why. So basically, that would end up in you doing two tests. One to say, hey, this is what I'm choosing to compare to, and it diverges or converges because of p-series or geometric series. And then we have to go back and compare that, do the actual comparison test. So this time it took two. Now, if you're doing integral tests, or if you have a geometric series, or you're doing ratio test or alternating series test, it would just be that one test. And I'll let you guys try a few, and let's just kind of look at a few of these too. Also, once you get better with these, which you guys are new to them, but I can look at these and kind of tell which tests I want to use. For example, I have a constant to an n power. This is going to be this is geometric. Okay, so if we're looking at one like A, kind of stealing this one from you, but if we have one like A, where it is just the series n equals 1 to infinity, 2 to the minus n, well, that is the same as 2 to the minus n. Well, that's the same as 2 to the minus 1 to the n. So this is basically 1/2 to the n. Anytime your general term is an exponential function, this is a geometric series. So this is geometric with a common ratio less than 1. So we know it converges. In fact, we can even find what this one converges to because we know how to do the sum of an infinite geometric series. So this would be one that would be not only just needs the one test, but is actually really quick because it is geometric. So if you get something that is geometric or is a p-series, it's very quick to say that it converges or diverges. These ones where you see the factorial, we know those are going to be ratio tests. This is on the alternating series part. And you can kind of take this as a given. Anytime you see a factorial in there, it's going to be ratio test. So we already know, if you see a factorial in there, that's our hint that we want to use ratio test. So we can go to the sheet, and ratio test is right here. The biggest thing is setting up your limit. We talked about this one last time. So limit as n approaches infinity. It's going to be a sub n plus 1, which is all these n's are going to become n plus 1s. You don't have to include the alternating piece because of the absolute value symbol. And you don't actually, because you don't, it's kind of like they cancel each other out. The -1 to the n and the alternating and the absolute value. We need the absolute value to make that positive. Because the absolute value makes this part positive, we don't need to write it. So I kind of, when we're just proving series are convergent or divergent, I don't often write the absolute value signs because we don't really need them. And so n plus 2 factorial. So this is a sub n plus 1. 2 to the 4 times n plus 1. Okay, we'll distribute that 4 in the next step. And here, n plus 1 is where the n plus 2 comes in. 2 to the 4n over n plus 1 factorial. Again, we could put the absolute value. What the absolute value does is it takes care of the alternatives. So this is what we're going to focus on. Once you have it written up, your main thing is going to be canceling. We talked a little bit about some of the canceling last time. One of them is, n plus 2 factorial is n plus 2 times, n plus 1 all the way down to 1, but that there is n plus 1 factorial. Now, the other thing that's going to happen is we have 2 to the 4 times n plus 1, which is 2 to the 4n plus 4, which is the same as 2 to the 4n times 2 to the 4. And then 2 to the 4th is just 16. We can take care of that later. So those are going to be the two things that we're going to do in these steps. I just want to put them on the side here just to preserve what we're doing. So limit as n goes to infinity, n plus 2 times n plus 1 factorial. We know this is going to be 2 to the 4n times 2 to the 4th. Keeps putting that cross on my 4s for some reason. And now what it does is it makes our canceling really obvious, right? Now's the fun part. We just start crossing stuff. N plus 1, 2 to the 4n, 2 to the 4n. Now, anything that's constant, I like to take out of the limit, which is this 2 to the 4. So I'm going to put 1 over 2 to the 4, or 1/16. Either way you write it, it's fine. Limit as n goes to infinity. And all we have left that depends on n is n plus 2. The constant is not going to make a difference in this. As n goes to infinity, n plus 2 goes to infinity. So we go to our ratio test. If L is greater than 1 or is infinite, the series diverges. Now, so our series, I'll go back to the question in a second. Now, here's what's nice about the ratio test on problems like this. This one asked you to figure out if it was divergent, conditionally convergent, or absolutely convergent. The ratio test, if it's convergent with the ratio test, it is automatically absolutely convergent. So because the ratio test gave us divergent, that's it. this thing is divergent. It cannot be conditionally convergent. Okay. A good example, B and C are good examples of ones that would be conditionally convergent. D would be absolutely convergent. And the reason is because B and C will converge with the alternating series test, but once you take the absolute value, they will diverge. And that can be shown with P-series comparisons. Similarly, D, we can show that, it converges with the alternating series test, but if we were to take the absolute value of D, in fact, let's go ahead and look at D. I want you to see what happens here. I know this wasn't the one you asked about, but I think we can take a look. So first off, clearly we have an alternating series. So we could very easily do the alternating series test on this one. But what I notice is I've got an n to the first over an n cubed. So if I were to take the absolute value of this series, basically that drops off the alternating piece. And we end up with n over n cubed plus 2n squared. And like we were talking before, we take the lead terms and we use that to write a series we're going to compare it to. So if we were just looking at n over n squared, excuse me, not squared, cubed, well, this reduces down to 1 over n squared. I'm not writing it, but these are all, n equals 1 to infinity. This we know converges by P-series. So what we'll do, again, I'm a fan of the limit comparison test, but you could easily do a comparison test on this one too. So we'll do a limit comparison test. So limit as n goes to infinity of n over n cubed plus 2n squared all over 1 over n squared. So we'll flip that denominator and multiply. And look at what happens when we do that. When we multiply by n squared over 1, that gives us n cubed on top over n cubed plus 2n squared. Now, again, we could do this saying, hey, horizontal asymptote of rational expressions tells us this is going to be 1. But if we wanted to, we could also use L'Hopital's because we've got an infinity over infinity case. This is more of a refresher. Again, you wouldn't need this one on this particular problem, but take the derivative of the top and the bottom. So 3n squared over 3n squared plus 4n. Okay, we still got an infinity over infinity case. So I'm going to use L'Hopital's again. Limit as n goes to infinity of 6n over 6n plus 4. All right. Once again, an infinity over infinity case. L'Hopital's again. You can use it as long as you still have your indeterminate form. And you get down to 6 over 6, which is just 1, which is greater than 0. So our series, negative 1 to the n over n cubed plus 2n squared is absolutely convergent. And I did use 2 tests, by the limit comparison test. And we could say the absolute value test, but what we tested was the absolute value. So you don't really need to say the absolute value test, but I'll put it in there because we did use it. Because if the absolute value is convergent, we know that the original series is convergent, and it's absolutely convergent. So it's almost redundant to say it's absolutely convergent and the absolute value test. The big one is the limit comparison test.